a set of discussions by the key leaders of each of the payloads, as well as on the mainframe systems, and then we will have two keynote addresses, which of course Professor Manchanda will chair that session. So we begin the first of these discussions on with UVIT. Professor Shyam Tandon, who has been the key person who's actually pushed through, worked hard for years along with his incredible team to realize a ultraviolet telescope, a large field, highest resolution UV telescope in the world, and we have been very fortunate to have seen the results from it. And so we invite Professor Shyam Tandon to say a few words. Everybody has only 5 minutes in order to manage the time. So if you could please come forward and address the gathering.
Okay, so here I hope to tell you something about UIT realization. So at the bottom, if you can see, the list of collaborating institutions is a bit too low, but you read maybe IIA, IUCA, Pune, from India, CSA, Canada, and all many ISRO centers. And there were some agencies we paid money for getting something, Photech in UK, Muller Laboratory in UK again. So here it is. You see the telescope configuration, the twin telescope, meant to observe in basically two bands, what we call far UV, the shortest wavelength here, 125 to 180 nanometer, other 200 to 300 nanometer near UV. And for tracking drift, we have added a visible detector also, but not for observations. Now, I can say, summarize in a few words, what is special. It just looks like an optical telescope. What is the difference? The difference is for two reasons. They already mentioned by Dr. Alex and Jaswinder actually, see. One is that the drift was a lot compared to the PSI we wanted, which we got 1.5 arc seconds. Other is contamination. The far UV, the shortest wavelength, is very sensitive. Even monomolecular layer can absorb a lot of light. So we take care of that. So let me come to that now. Some few points about these two. Okay. For you again, I mean, you have to make all the tests in the vacuum only. It can't be done in the normal air. The coating has to be different compared to optical telescopes. Can you hear me now? Okay. Detectors. You see, the point is they drift, so you have to take very short exposures. And hence, you have to have zero read noise. So CCD can't be used. So you have to intensify detectors, intensify imager. And there's some technology difficulty. They photocathode high voltage and the MCP. So typically, the gap they 0.3 millimeter between the photocathode and the MCP. But you will not get 1.5 arc seconds with that. So we have to reduce the gap, make a lot of tests so that the photocathode then collide with the MCP, not the high voltage discharge. Took some effort to get it right. Not too much, but it did take some effort. Different pointing, already mentioned, a lot of drift is there. So we take short exposures, already mentioned with Dr. Alex earlier, and then put them together by shift and add method. Typically, exposure about only 30 milliseconds for each UV channel. Flat field calibration, ideally, you should shows moving around very carefully, accurately in the field. But there's some difficulty with exact pointing. We could not do it actually. So we had to use a dense field and shifted it around and did calibration. Not the ideal way, but I think we got it right after some lot of effort. Cosmic showers. Surprisingly, every 200 milliseconds you get a big shower of cosmic rays. Hundreds of photon-like events. We don't know what it is, of course. So we have to get rid of that. Makes a lot of background. Very substantial far UV, which are very few photons actually. So you discard each and every, you look at all the frames, see that number, and then discard it if there are too many photons. Some of them will leak through. You will also lose some genuine frames also, not many. So you carefully design the procedure for that, and we could get rid of all that with a very substantial background actually. Then this was the real challenge. As I say, monomolecular layer can absorb a lot of radiation. So fortunately, the project was born with sensitivity. People were very conscious that this is going to be a serious problem. The laboratory was made in IIA, which could test materials, components, then have assembly procedures in clean condition, monitor the conditions in laboratory, each location, wherever you store things, assemble, and people have to be also kept some protocol. Now, so as I said, so it's an invisible enemy, so it took a lot of time actually. And actually, we spent a lot of time convincing everybody in IIA and ISRO, many places. This is a very serious matter, and we have to take care of this thing right from the beginning till even today. Even now, as Jaswinder explained, how to avoid sun, because solar UV radiation can do some damage. So it continues from beginning to all the observations. So it's continuing even today, actually, in principle. You can say that. You see, coating. Normally, coating is some kind of organic material involved in coating, black coating. So that was a danger. So a special coating had to be developed, inorganic, which was done by thermal group in URSC, and Dr. Sharma was there. He very quietly did it once he came and told us, I've done it. So very good. So you avoid only because very large surface is there. All the mechanical structure, tube, etc. They have a large surface, and that can lead to a lot of contamination at any stage. Okay. Illumination, all the places are kept free of UV. Nowadays, we have LED. Earlier, the tubes were there, the fluorescent tubes. There was a filter available for that. You avoid that. So now, at all stages, you see that wherever you put any component, you make sure that environment is clean. So we put witness samples. If you have a mirror somewhere, put any samples or somewhere there. You test it every week, every 2 weeks, or whatever. And then when you assemble, you purge it with nitrogen gas, clean nitrogen, and monitor the nitrogen coming out of the cavity, whether it's clean or not. In fact, on one occasion, we found out a problem. The being purged, nitrogen was not very clean. So we found the problem with the witness sample. So we changed something anyway that happened. All that, and then doors were kept closed because after launch, there were doors. I didn't explain the picture initially, and I'm sorry I forgot that. The doors on the telescope, and they were not opened till 6 weeks after the orbit was obtained, because other instruments in satellite, they evolve things, that can contaminate. So you kept 6 weeks closed, then opened it, and 6 weeks, and enough, fortunately enough to keep things clean. Now all the maneuvers of satellite were designed to avoid any scattered radiation of sun or bright earth. So when moving, I just gave he showed some picture. You have to avoid any scattered light from sun or earth. So this is protocol developed by the group in URSC, and it has worked well so far. Okay, so whatever we did, it has, I think, worked even till today. They know measurable decline in sensitivity of far UV detector. It's certainly not more than 5% 10 years. Probably nothing there. So I think I will end here. I want to show what was the issue now. So this is how people are working every day like that. They totally covered. There will be witness samples somewhere in the vacuum chamber, maybe in the room. Whenever any component which came, we tested it. Materials we tested, they were set up for testing materials. And I think we had got motors done by IISU. Initially, we had a lot of problems. Then we worked with them. They got clean motors. They tested. Motors were tested, set up. So like that, we worked on that. And I think to get it right, because the level of cleanliness required was totally different. Whatever is known in ISRO or us is 100 times more sensitive. No, the thing was that everybody agreed actually, very nice. Any problem we said, hey gentlemen, they all agreed immediately. That I was quite impressed by that. Say, look, this is not okay, this is required. They will start working, corrected. With all the cooperation, a lot of work was required. Finally, we got it right. And I hope in the future there will be less difficulty in such payload for your cleanness. Okay, I will end there.
The challenges involved in actually building this amazing X-ray mirrors as part of the SXT payload. As you know, it's the first time we built such a mirror in the country, and Professor K.P. Singh has been tremendously instrumental in getting this success.
Okay. So it's a great pleasure to be here and to talk about what we did for the SXT. This idea to make a soft X-ray telescope actually was born in '79, embedded in my mind when I first met G. Srinivasan in a conference in NATO Study Institute in Riche. And subsequently, I spent every opportunity to learn about doing X-ray optics, whether it was in Denmark, and when they were making spectrum gamma, or Nagoya, where they're building, other satellites and so on. So anyway, I will quickly go through. This is the basic structure of the soft X-ray telescope that we built. It had many, many components. So you have parallel beam, which goes through the, mirrors, in gold mirrors, which we had to build and for which we make a clean room and learn how to make replicated thin foil, lightweight gold mirrors. And so the whole thing was built with 12 kg module, and then the optical assembly and for testing and so on. So everything was a new learning experience, but one had to persist and go through it. And then, the mirrors were not perfect hyperboloid, paraboloid. They were conical because they didn't have the stiffness, because they were very light. And then the CFRP tube, for which Kiran Kumar, he's not there, I met him when he was making AstroSat, and he says, go to the Trivandrum composite assembly, where they make composites and so on. And that opened doors for other payloads to carry on. And so we built the tube and all the structures and mechanism groups and so on in ISRO. They helped with various mechanisms, especially the opening door on the telescope. The mirrors, which we had to, for which we didn't have a CCD because it was too expensive, beyond our budget. And we had a collaboration which was talked about by Koteshwar Rao today morning. And but we got the design from them, but built the camera entirely in India. And for which, again, we had to go do a lot of running around and do with the how to make a gold coating inside the camera, etc. So, but we got the chip assembly and we put it in. We modified the design and built it and so on, and then we built the inside. So everything was almost built in-house. So this was the gold mirror, and as you also heard that UV requires smooth mirrors. Well, the X-ray require even smoother mirrors. So we had 7 angstrom, and this was, we did the testing at Raja Ramana Center for Advanced Technologies in Indore, and we qualified the mirror roughness. And then finally we built 40 conical shells, each to be placed behind each other in a perfect configuration, and they were built in quadrant by quadrant. So there were like 320 mirrors to be aligned perfectly behind each other, so that they are confocal and coaxial and so on. And that was another challenge, was that how to do that, and we had to find a good precision machining which would put that in a configuration, and the distance for each shell is different depending on the angle of grazing angle and so on. So this was the thing that we had to make on the side, which was we made as accurate as possible with a single setting, cutting, EDM cutting and so on. And the problem was the ribbon would burn out and so on while the cutting, but it had to be done, and that was done in Bombay in a very interesting institute which had a good machine, better than TFR had, and so on. And those people came forward and said, oh, I'll make it for you. And it was an electrical design machining and so on. So even the sputtering system we had made for the gold was first time in India that anybody made an automated sputtering system. And that was 2000, the beginning of the whole thing. But it took not just 6-8 months, as somebody pointed out, it actually took 6-8 years to make all the mirrors, and because the success rate was quite low in replicating the gold from a glass surface. So it was a replication of a very smooth glass bought from Schott in Germany, and then replicated onto the gold surface and transferred to the aluminum foil and so on. And that's where LEOs came in and said, no, you test the adhesiveness. You have to pull and see how badly they destroyed. Yeah, done. And then this is the whole thing which was delivered. This was the camera. And then it was tested for qualification and so on, individually, then all together. And today, then we opened, the camera door was opened, quite late, as for the reason that Tandon just pointed out, for outgassing and so on. And we had the first light, and I was amazed that we could actually see the X-rays focused on the mirrors, because so far I'd done only the inverse optical telescope to check the mirrors and not the X-ray thing and so on. And today we get resolution which is comparable to any satellite, X-ray satellite. And this is the latest calibration, low energy, high energy, and you see the perfect fitting to the internationally recognized, called iCheck model. There is a consortium, and which Vadim is a member of that. And so we have that model, and this is a modeling of 2 supernova remnants, and you see all the lines perfectly fitting and so on, calibrated. So, yeah.
Thank you. Thank you.
Welcome.
I now call upon Dr. Professor Y.S. Yadav to really tell us about LEX-PC. As you know, LEX-PC was an instrument very close to Professor P.C. Agrawal. I mean, he began with that as his large area and the largest area systems were built, and with Professor Manchanda playing the role in between. And finally, Professor Yadav will tell us how he finally delivered that.
Thank you very much for organizing this meeting. I'm very happy that we have been working very hard, and today we are seeing what is the advantage, what is the use of those. So I will be talking about a large area proportional counter. I assume people know this, so I will just directly go, because since this talk is for 5 minutes, I assume that people know this proportional counter. It is a large detector, 5 layers, 15 by 100 by 40. So it is a large detector with at 2 atmosphere. Professor Agrawal already told some problem, and so I will be talking about the problem after that. So LEX-PC instrument developed is led by P.C. Agrawal up to 2011, then Professor Manchanda 2011 to 2012, and myself from 2012 to 18. And launch, of course, this was 28 September 2015. So just to remind you, LEX-PC instrument, of course, the large payload, something like 9 flight packages, and 430 kg. Of course, 3 identical detectors are used to provide large effective area for broadband spectroscopy with fine time resolution of 10 microseconds. So we were supposed to achieve these things. It is developed indigenously, designed and developed indigenously in India. We faced a lot of challenges, issues during this development. I will describe few, to be named only 3 or 4, because there are many, many challenges. I will be talking about only 2, 3. And beside these challenges, of course, we put efforts for its calibration, change the calibration unit, calibration, then simulation, and then background. In fact, those are paying now. And so it has been that way successful in comparison to outside the instruments. HXT from China, nicer, our timing is much better. And then New Star, for our efficiency is much better for non-thermal emission. And you will see that we have discovered recently one new type of burst in GRS 1915. This is 26 years history of GRS 1915. this is discovered because it has the capability to discover that. No other instrument has that. So I will just quickly go that most of the tests were done during July 2013 to December 2014. Red shows the failure, so there were failure before that. And in bracket, you see that some instrument, of course, we crossed the successfully some test, but when we reached the calibration, we find in calibration some issue, and then we have to change something, then we have to go back to the, again, vibration test and those things. So I can show you one such thing, like we were testing our, one of the detector, and it was all calibration, space qualification tests were done successfully, no issue. When we were doing calibration, then top layer, odd, even, they have two separate output. And when we were calibrating with iron, one such things gives the clear number of photons coming from iron, others is 0. So now then we have to remove from the calibration, bring it out, understand, and it was the gain of ICs, because both ICs should be matching in gain. And again we changed, of course, then we have to go through again the whole cycle. So this type of the things. So most of the tests were done from July 2013 to 2014 successfully. The LexBC instrument developed was facing serious issues in 2012. There was some issue in this because there was failure of both PE and STVG. And then at that time, we fabricated the new cards. But when these cards came, it didn't solve the problem. Then we have to start again from the lab cards, what are the issues. For that, what I have to do, I decided at that time that we will keep the instrument at least for 15 days in vacuum and see. It should work continuously. In fact, we spent 15 lakhs on that. And then, of course, the many of the new issues popped up. That may be during either front-end electronics, detectors, or processing electronics. And since it has no prototype model, then we cannot check in prototype. So we have to go to lab cards and check where is the issue. Because we cannot play with the flight detectors or processing electronics. So these many new issues popped up during this time. That was during 2013. We were very hard working at that time. Capacitor issue, port resistant issue, purification issue, IC issues I have already described. Then label noise, ground issue, clock speed. Of course, we changed from 24 to 16 to solve some certain thing. And then PE issue and many others. Now, one of the issue was the purification pump. And that was also happened at the last moment when we were doing calibration. Before each calibration, we were purifying so that we get good energy resolution. So you can see that top, after this problem was there, we have to do it putting in some nitrogen environment and correcting it. Once we corrected it, you can see on the other side that before purification and after purification, there is a great improvement of resolution. And my opinion is this, of course, we were using this purification for first 2 years. If we would have used this routinely, then probably we would have avoided what happened to detector LexBC10 if we have used this systematically, because that was the thing, this purification at ppm created a lot more issue there. So this is really for the management to take this lesson. Now, another is, of course, when we were working on the PE electronics, and you can see that top was the when commercial MCA was used, that yellow, and then down red, you can see when we got PE, of course, all resolution in whole range is improved. So that was really the benefit we got. And of course, A10 bit layer, it didn't work. There was issue. Of course, we have to work on this, why it didn't work, what are the problems, what are the possibilities. We talked about this. And ultimately, we have to find out what is its effect. Effect was 15 counts in background. 150, instead of 150, it was getting 165. And we then go for it. There will be no issue, and we can live with it. So beside this, now I will just show what I feel, what is the contribution we have got in science from LexPC instrument. So this first, third, fourth, this is many papers you will see in this conference, that is fine. Cyclotron, this NS equation of state, third one, and the timing in spectral studies in origin of QPO, especially origin of QPO in the origin of high frequency QPO. I think there is a significant progress from this data. It has significant capability there, it has significant progress. Discovery of new X-ray class, GRS 1915. This is 26 years of GRS 1915. This was the first time this particular class was this, and it was different than any other class. And it is due to the capability of LexPC unit, LexPC detectors. No other detector worldwide can detect this. Then I'm coming to solving the puzzle of course, this is not done, GRS 1915, and I feel it should have solved this, okay? But it is not yet done. I hope that people will work on this and it should be done. My only issue is here, I just want to put a comment that this 26 years of GRS 1915, there was only one outburst, and AstroSat was in great opportunity. Only this instrument studied its decay of this outburst. But we have not taken sufficient observation. Otherwise, we would have solved this issue. So I think this management should see why we have not done. I think that is a very important issue. And from large number of research papers presented in this conference, I can conclude that LexPC instrument has achieved its science object. Thank you.
We now call Professor A. Rao to come and tell us about the last instrument that got onto AstroSat, which is a cadmium zinc telluride detector, a new technology of compound semiconductors, which has subsequently been used in multiple missions beyond AstroSat. So, Professor Rao.
Well, AstroSat is working for 10 years. It's a proud moment, happy moment, and very nostalgic moment. When I see many people who worked together during the early days, I really feel happy. I mean, I don't want to name, then it will be the whole 5 minutes will go in that. And as Professor Agarwal has rightly said, this is particularly the X-ray instruments, is the culmination of 50 years of X-ray astronomy working. Many of them worked from the beginning, is the culmination of that. Now, if I want to summarize the challenges of making this instrument CZTI, I'll select only few of them. Challenge number one, even getting the CZT detector. Because during design, the major X-ray instrument was LexPC. Okay, in the between 10 to 100 keV or 5 to 60 keV, it is the larger detector. At that time, it was decided to complement, to get wideband spectroscopy, we need soft X-ray, very good spectral detector, and high energy we need to extend up to 100 or 200 keV. Now, at that time, 2000, this near room temperature detector was just emerging in the market. People are saying that these are the detectors of future. And based on those detectors, it's a good idea to have a large area hard X-ray detector. But of course, it's an emerging technology, not many vendors. Remember, it was post-Pokhran 2, severe embargo. Even some of the major detector people who are fabricating were not even replying to our emails, okay, like EV products in USA. Finally, we have to make do with a commercial product from Israeli company who are barely developing it for the lab purpose for medical technology. It is not known that it will work for spaces. So we took interest, got them, did a thermovac, satisfied it's working, and from that one example, audaciously went and planned this whole 1000 centimeters square hard X-ray detector. And getting the detector, making this delicate detector working, getting itself is a challenge, making it work. That first challenge it was crossed. Now, second challenge, because it's a commercial detector, large area, everything has to work, and in space is very unforgiving. How to get space heritage, okay? So one thing is that, okay, think carefully, make it well, and send it up, it will work. No, I think there are many intricate things which generally come from experience. So we worked, so for example, these are new detectors, okay, and typically we need 64 such delicate modules to make 1000 centimeters square. From design itself, make it quadrants so that there is redundancy. Even then, very small detector were sent in GSAT-2 so that how to use the CZT detector we get an experience, this is a PRL experiment. And similar CZT modules were hex detector on Chandrayaan-1. Most importantly, with the close collaboration with the VSSC, we sent these RT2 CZT detectors, which is 3 modules exactly identical configuration, including the new coordinate aperture mask. So getting the space heritage, managing multiple projects, along with making the AstroSat, it was very challenging, but it was done. That gave us a very lots and lots of confidence. We could be very confidently say that this detector will work. Now, third challenge is a bit intricate. Many people worked for this instrument. I mean, TFR, of course, and electronics, everything was supported by VSSC Trivandrum, closely worked with that. And RRI, IUCA, IIT Bombay, PRL. You can say that putting everybody together would be a big challenge. No, that was the easiest part. I found that people are nice and gentle. You approach them nicely. I think everybody wants to contribute something nice. For even when we came to URSC and thermal, mechanical, the collaboration, getting people together is the easy part. But what is the most difficult part? Most big challenge is that how to make it 100% perfect, 0% failure probability. Because I have done many space experiments, many of them failed. RT2 experiment, which was designed and built very wonderfully, after 9 months, power supply failed in the satellite power supply. So no serious result. So how do you make an instrument work with 100% confidence? So even in 2013, I was personally not confident, but miracle happened. I think 2013 to 15, all of us, scientists, engineers, we gathered in URSC. And there is no ego. If there is any problem, we went to the bottom of it, okay? And there is no blame game. So this cohesive work of 2 years and everybody for one particular purpose working together, that made AstroSat and CZT successful. So when people said today that it was designed for 5 years, it's surprising that it worked for 10 years, no surprise. This is basically the results of engineers, scientists, management, everybody in one single purpose working together. In that sense, this is the final challenge for any space experiment, but large number of experts with one single idea working together will make things successful. This is the first image of CZT crab image. Okay, thank you, sir.
The Scanning Sky Monitor played the role of a watchdog looking for transients in the sky. Dr. Sita was the initial first PI. For years she has worked right from the early days of discussion of AstroSat, and subsequently when Rama was a student working on SSM, now she's actually leading the SSM project. So tell us about challenges.
Thank you, Dr. Shikumar. Good morning, everyone. It is a very happy occasion today, a very proud moment indeed, celebrating AstroSat's 10 successful years of operation and a lot of accomplishments. So I take the pride here at this moment to present to you SSM. Dr. Sita is here, who is the first PM of SSM. She started it from the drawing board, and I joined her a few years later as a student. As Dr. Shikumar was mentioning, I did a PhD under her. And it is about the design, development, and calibration of SSM. So SSM, as everyone knows, it is a wide field X-ray sky monitor. It's a one-dimensional imaging instrument. And as compared to other instruments on board AstroSat, this is unique because other instruments are pointed mode instruments which all look at one source continuously, while SSM has a very wide field of view. So the field of view is 100 degree by 20 is a rough number for the 3 of them. You know, each, the center one is a larger field, 26 by 100. where the side edge cameras give 22 by 100 degree field of view. So the three of them are mounted on a platform which is capable of rotation from 5 to 355 and vice versa to cover the sky, 50% of the sky in one rotation. So I would like to mention that all other instruments on board AstroSat is proposal driven by users, whereas this continuously observes the sky on its own. And the standard mode of operation was step and stare, step for 10 degree, and then stares the sky for 10 minutes. That was the standard operation. So I want to mention that every element of this was indigenously done within the ISRO centers. So URSC taking the lead, all elements was done within URSC. The platform, which came from the composite section of VSSC, a lightweight platform, honeycomb structure, on which the units are mounted. So AstroSat, when all instruments get integrated, SSM on its own was a detailed integration which is done within URSC. So, and here I highlight these points. So it is a 1D position sensitive gas field detectors and the gas mixture that is on its own a research. You know, we initially it was a P10, then we had to do different proportions of gas mixtures to choose and finalize on this. So it's an epoch of experiments and tests to finalize on that. And the gas pressure has to be just above the atmospheric pressure because, you know, I'll take you to the next slide where we will show you the wire module, which is really a challenge. And to make it happen was a miracle. And these are the elements, like 60 millimeter was the length of the anode wire. And I highlight the diameter of the anode wire, which is less than the width of your hair. And you just imagine handling such wire modules to make the instrument. So this is an image photo of the wire module here. So there are 3 units. So this is one module which is placed inside the detector. So this is not working. Okay, so this is the one wire module wherein you see the circular white ones, those are all anode wires at the center, and the cathode wires form different array. So there are totally 20 cells. Each cell is a individual independent proportional counter. So it's like handling 20 detectors in a module. And so 66 plus 20 anode wires, which is 86 microns wires, diligently wired. The wiring mechanism was done in-house. Mr. Chandrababu here must be watching this. He was instrumental to do this brilliant effort of making this happen. And once this wire module is done, when you fill it, put it in the gas detector, fill it with just about an atmosphere. And then, after filling, when you want to test it, if there is a slight differential pressure, the window on the top can go inwards, meaning bulge in, which can snap all the wires. Making the wire module takes months of effort. And just a small mistake, it has happened. And it snaps. And so, making 3 such detectors on its own was a difficult task, but a brilliant team effort that we came across. And next, I would like to highlight this, sealed detectors. Such small volume, lakh species is a huge volume. So a micron leak in the gas, huge volume, may not make a big difference. However, the gain has to be maintained consistently for a long period of duration for the detectors to be efficiently working. 1 more minute. So having the gain stability without any leak for the small chambers was really a difficult task for us, and all the team had to toil a lot. And finally, we achieved it. This is a figure here, the one on the right top. For 3 years, the stability of a detector was tested, and it's not one detector. We had to do 3 detectors like this, establish the stability of the gain, and diligent calibration of the instrument. So the one on the top, the one below this point is not working. So the one here shows the energy resolution, and this is the position resolution, and this is the efficiency. So each of this anode wire, a cell in the detector, has to be tested for efficiency, position sensing, energy resolution, and taking it forward to imaging, the next one. So efficiently, this instrument has to do wide field imaging. So with all parameters in the detector, you need to image the sky. So this coded mask, Professor Dipankar has been instrumental in doing this coded mask image along with algorithm. So on ground, when we test, ground is so easy, as Professor Rao was saying, space is a really difficult task to maintain. So here, this is a ground calibration where we were well assured that imaging is definitely possible, because with any imaging we do, we could get the position as well as the flux. Whereas when it was launched, the scenario is different. You have a large background. The wide field, 100 degree by 22 degree, as compared to 1 degree of other instruments, we have a swamping background in the detector. In spite of it, we could do the imaging, and that was the first slide shown there, which is observation of the Crab Nebula. Crab Nebula, as you know, that it is not a crowded field. It's a sparse field with a very bright source, so we could easily image that. However, the other regions were in crowded regions. We still able to do that, and we could capture bright transients in outburst, and few astronomy telegrams have gone indicating that SSM has detected transients, and 2 or 3 follow-ups we could do with AstroSat. And there are few ATLs published in this. And with 3 instruments, 2 of them with reduced efficiency, 1 is switched off. The other instrument is still going bang with the same efficiency continued. Thank you so much, one and all, for the opportunity.